Okay, so this is quite a long lecture. This is why I prefer to split it into three parts. So we have seen PD controller with gravity compensation, with gravity cancellation, PID with saturated error in the integral term, and so on. I would like to conclude this lecture on regulation mentioning a number of limitations of this type of approaches and introducing, therefore, a practical way used mainly in industrial robotics, but you can use it also in your research activity, on how to design a regulator for this type of task, which try to avoid the limits that we will now illustrate. So the first limitation is on response time. You have seen in part this in the simple simulation that we have shown. The regulation of an inverted pendulum took something like 3 or 4 seconds, which may be too large a time. Okay, and in general, these response times are not easily predictable, even for a given robot. When you change the task, even if the amount of motion is the same, but you change initial configuration, because of the large changes in inertia for the different configuration and of the action of gravity in general, which is configuration dependent, the response time of this nonlinear system may change quite a lot. This time depends indeed on the particular choice of the PD or PID gains and on the robot dynamics itself, the robot workspace. Remember that if we have sufficient condition for our gains, the fact that we satisfy them is only a guarantee of asymptotic stability, but not of transient performance, so having a fast response time. There's another aspect when we are dealing with the integral term, when it's present. This tends to makes longer final response time, because in the integral term we load all the errors of the trends. So even if the robot is starting from the beginning and going in the direction of the desired configuration, so everything is working fine, still we accumulate error. So when we get closer to the configuration at the destination, maybe the integral term is overloaded with this error and needs to discharge part of the torque, because at the destination the torque needed to balance the gravity may be smaller. We know that at steady state, for sure, the integral term will compensate the gravity in the configuration desired. So if there's too much torque stored in the integral term, there will be problem. This is why, even in the current automation practice, not for robotics, there are many anti-wind-up schemes that stop the integration when something happens. You can start integrating only in the vicinity of the destination. This could be one idea, actually quite interesting. Or if your commands during the initial transient, and we will see that this is another issue for this type of controllers, saturates, indeed there's no sense of accumulating integral error when we are in saturation. So there are anti-wind-up schemes that avoids this process in an automatic way. By the way, the fact that the integral term is too loaded, and this may at least slow down convergence, if not bear at all asymptotic stability, is also an intuitive explanation for the success of the saturated version of the PID law. In fact, the saturation is only on the integral term. One may also consider the fact that in practice the actuators have some limitation, and if I want to prove that a PID or even just a PD control in the absence of gravity works, I should take into account the presence of this saturation. So I should have a function which says my controller is a PD law saturated as a whole, so putting an upper bound and a lower bound on the maximum amplitude of the control torque. So we have not done this, but this can be done. If you're interested, just contact me, I can provide you the reference. So response time is one of the main limitations of such regulation controller for robots. The second one, which is, I would say, even more critical, is the requirement of the control effort. Because the error is typically large, and it's large right at the beginning, because when the robot is at rest somewhere, it needs to move some other position where maybe it should pick something and then place it somewhere else. Now this initial error with gains that tends to be large, because we understand that larger gains means larger action by the controller. So in the hope that this will reduce the transient time, we choose larger gains, at least proportional terms. So in the first few instances we have large gains and large error, and will typically exceed the capability of the actuators, and certainly the torque needed at steady state. And we have seen this already in the simulation for the pendulum. So especially when positional gains are chosen high. And the other aspect is that if you consider the physical limitation of your actuators, you will saturate this, and this is a hard nonlinearity, and the analysis that we have done so far, in principle, would not even be sufficient to prove asymptotic stability in the presence of saturation. And of course, bringing the robot actuators always in saturation during this transient is also not good for the wear and tear of these devices. So, what happens in the industrial world? Do they have all these problems? In fact, they don't have this problem. They are not interested in theoretical proof, but in practical operation. While the idea that is behind the practical proof for us is to really understand the nature of the problem, of the control problem for robot manipulator, and suggest new ideas. So this idea is quite simple. So in industrial robot, even if your task is only a regulation task, so you're only interested in being in some configuration and typically at rest, you don't care how you get there, provided that you go there, let's say, fast enough and without requiring too much torque. So exactly the limits of what we have seen so far. So even in the case where QD is a constant reference, the trajectory planner is being called and generates a reference trajectory QRT, which will bring the robot from the initial configuration to the desired constant configuration. Okay? So even if this trajectory has no sense, has no practical information, no content in information, so we have not to follow a path with the tool in the end effector space, it's just a mean to get to the final position. Why is this useful? First of all, the reference trajectory can be chosen smooth enough. We have seen that polynomial type function, cubic or quintic polynomial, or even other things. But if we plan a trajectory between one configuration and the other, we can also define a transfer time. So how much we expect to spend in that motion. Let's call this capital T. So this reference trajectory will has a boundary condition, certainly that at time zero, the initial start of the trajectory, the reference is equal to the current configuration. So I'm starting with zero error with respect to this trajectory. And this trajectory will get at time t at the desired configuration QD, and from there on will vanish, will stay there forever. So it's just an interpolating motion that I'm fitting to the particular point-to-point task. The role and form of this is practically irrelevant. Of course, I will use something that will let the robot not wander around its workspace. So I'm using polynomial type trajectory, and I'm imposing also boundary condition for velocity and maybe also for acceleration set to 0 and so on. So once you have designed this reference trajectory, you apply any of the controller that we have seen so far. A PD plus gravity compensation, a PID, or gravity cancellation, and so on. For instance, if we are using PD with gravity cancellation, now we replace wherever there was a QD or a QD dot which was 0 because QD was constant, you're using the reference trajectory at the given time and its derivative, which is typically non-zero, which is non-zero in fact. So your PD plus gravity cancellation looks like the one in the yellow box, Kp times Qr of t, the reference trajectory at that instant, minus Q at that instant as well. So I'm putting a dependence on time only where I would like to show that this has changed with respect to the previous case. And then you have a Kd on the velocity error, which now is really a velocity error, although sometimes the terms Qr dot is being neglected in industrial practice if it's not too important. So what are the advantages of this? First of all, when you start, now forget about gravity cancellation, no? Because this is there for sure. So just for on the PD part. Initially, the velocity and the position is matched to the current position and velocity. So the initial error and its derivative are both 0. So the large effort that I would have if I would see at the initial time the full error Qd minus Q is eliminated. Now, the second point is that indeed we have no guarantee and we cannot prove that we will follow this reference trajectory. It is likely that we will stay in the vicinity of this trajectory while moving, in particular if we choose large gains. So now we are allowed to choose a large Kp because the error is 0 and will remain small, and if remain small I can use a larger Kp without going into saturation. So it's a kind of a chicken and egg problem, no? So the smaller the error, the larger can be the gain. The larger is the gain, the smaller remains the error. Okay. Moreover, since we remain in the vicinity of this reference trajectory but have no guarantee at all, and in general will not follow the trajectory, the reference trajectory, when we are getting at the nominal final time of motion, so at t equal capital T, there will be some residual error. But this error is small, so at this point we could tune the gains according to a linear approximation and have the best possible final transient. Okay, so we get many practical advantages in using this type of law. So this type of reference trajectory even in a regulation task. And this is the last aspect. So let's see this from a qualitative point of view, and then we will conclude with a numerical simulation to say also some quantitative aspect. So the idea is the following. If we give to a PD controller, now with gravity or without gravity, let's suppose that gravity is there. So the evolution, the qualitative evolution of the motion will be from an initial value q of 0, and we will get there oscillating and taking a long time in order to reach the final QD. At the same time, the control commands initially will be very large and then only eventually accommodate to the final desired value, which is the one that compensates gravity at the destination. Now, if we use a time varying position reference, interpolating in a given planned final time, capital T, the initial and the final position, for instance, the dashed red curve that goes from Q0 to QD, then initially the error will be 0. We will not necessarily follow this trajectory, but the actual trajectory of the robot will, this is just one joint, one representative joint, will oscillate around, and then when the final planet time is reached, the reference becomes constant, and so we are back to the conventional regulation task, but now the initial error at time t, so for this final transient, will be small. At the same time, because we never get large errors, and possibly we can use large gains, you see that the qualitative evolution of the torque is the one in the last plot on the right, so the initial torque is much smaller than the previous case, and sooner we'll get probably to the final desired value when we compensate gravity. So, summarizing, little chance, or no guaranteed, but in general no saturation of commands, and much larger gains can be used, and also better prediction of the settling time, because we have assigned a time t, and the remaining transient from t beyond will have local exponential convergence if we design the gains using the linear approximation of the robot dynamics around the configuration state, the desired state, so with the configuration QD and zero velocity, exactly because we are at this point very close to that state. So both conditions are guaranteed. Indeed, control gains require still a fine-tuning, but now this fine-tuning is easier because it's independent of the amplitude of the motion. Of course, it will depend on which part of the workspace we are connecting between the Q of 0 and the desired QD, so which type of changes in the inertial and gravity terms we are facing during this motion. So, let me conclude with some quantitative comparison. I've taken the simplest case with no gravity, so a planar 2R arm with this data. The first link has a mass of 10 kilograms, the second of 5 kilograms, equal link length, uniform mass distribution, and some value for the inertia around the center of masses. So the links are uniform thin rods, no gravity, and the motion is a rest-to-rest task from the straight configuration, so 0, 0, the one in dark green, to the configuration given by pi over 3, pi over 2, which is the light blue one. So this is the motion that we require, as I said, in the horizontal plane. And since we want to make a rest-to-rest motion, we choose as interpolating reference trajectory a cubic polynomial, so with the boundary condition equal to 0. So we have 4 boundary conditions. A cubic polynomial for each joint are sufficient. Now we consider 3 case studies. We start with relatively low gains, so Kp 80 and 40. The first gain is larger because remember that this we use to drive the torque of the first joint, which needs to move the whole structure, so it sees masses and inertia of both links. So typically the gains of the first joints are larger than the gains of the joints of the distal joints in the serial kinematic chains. And it's over-damped because the choice made here, this is a study made during a small project, probably were too large, so that we are damping too much motion. And the interpolating trajectory is here built of duration of 2 seconds. By the way, it's clear that this duration should be chosen in a suitable way. If we choose an interpolating trajectory instead of a constant reference QD, and we choose as target motion 1 millisecond, of course this will bring no benefit because we are moving instantaneously from the initial configuration to the desired one, and this is like having a step response. So we should allow enough time, and this is also a choice that is based on the actual dynamics, so the information that we have about the robots. So here we choose 2 seconds for doing this motion. The second case would be with medium gains, and this would be very over-damped. In fact, you see that we are using the same values for KD as for KP, joint 1 and then of joint 2. And finally, we increase largely the gains. You see in particular the proportional gains. We reduced in proportion with derivative terms. And we use an interpolating trajectory which is faster, 1 second. To make the simulation more realistic, we have introduced in this case also saturation of 30 Newton meters for the first motor, the first joint, and 10 Newton meters for the motor at the second joint. So this is the first case, let's say with low gains, and you see that on the first 2 rows you see the behavior with a pure PD, there's no gravity in this case, and a step response, so a constant QD. You see that the red value at some instant where we start the simulation, it's not time 0, it's 1 second. We move from 0 to 1 radian for joint 1, and from 0 to 1.5 radian for joint 1.657, so pi over 3 and pi over 2. And you see that there is no overshooting. This is because the system is over-damped in a sense, so we have used very large KD gains. Remember that they play the same role as viscous friction on the dynamics. But you see that there are peaks for the torque in the first few instants. And at steady state, they go back to 0 because, in fact, there is no torque needed to stay at rest in a generic configuration in the absence of gravity. While if we use the interpolating trajectory of duration 2 seconds, you can see that the blue line, the actual motion of the 2 joints, is pretty much close to the red line, although at this level of resolution you don't see the error which is present. But mainly has been a large reduction of the peak control effort. In fact, we reached almost 100 Newton meters and almost, say, 60, 70 Newton meters in the case of step response, while with the interpolating reference trajectory, we have maximum torques of about 7 and 2.3 Newton meters, and essentially with a similar transient duration. In the case B, very over-damped with medium gains, so larger than the case before, same story as before, and you see that the peak reduction is even larger because we reach almost 250 and more than 150, the full scale would be 200 Newton meters for the second motors. In the case of constant QD assigned from the beginning, while we have more or less the same maximum value as before for the case in which we use an interpolating reference trajectory. With larger gains anyway, larger than before, so this medium value, we can see that the following of the trajectory is quite similar. Now pay attention, we are not imposing any restriction in this case to the maximum torque. And finally, the last case, and by this I would like to conclude this long lecture today, we can see that with PD gains very large, so very large proportional gain in particular, you can see some overshooting in the first joint. This is because we have reduced a bit the derivative terms, so the system is no longer overdamped. But you can see that there is saturation for a few tenths of seconds in joint 1 and also in joint 2. Whereas in the case, although we have chosen a faster interpolating trajectory with just 1 second of transient, because of the larger gains, we follow them pretty much close, and even the peak torques are below the maximum level. So we have no peak torques in the first case just because we have saturation. But in the second case, we have just 1 instant of saturation of the first joint and no saturation of the second one. And we have all the best of all the worlds, so we are keeping the system below saturation, and in any case with low maximum torque. The transient is fast enough, even faster than the previous case, no overshooting. We don't care about any error along the trajectory. I'm not showing this because the only thing we were caring here was the final destination, because this remains a regulation task. And with this, we conclude today's lecture, and thank you for listening to this long recording.